Welcome to Dr. Boxy Teaches Electromagnetism. Today I will discuss three topics with you. First of all, we're going to look at the gradient, the divergence, the curl, and the Laplacian as they are described in the new coordinate systems we learned about in the last lesson. Afterwards, we're going to look at something known as the delta function, and finally, we're going to discuss the Helmholtz theorem. This will be the last introductory lesson in mathematics. From the next lesson onwards, we can actually start with our study of electromagnetism itself. So let us get started. We start with the definition of the gradient in Cartesian coordinates. It's a vector whose components are the partial derivatives of the scalar field t. Now, if we work in the Cartesian coordinates, that's fine. We can use it as it is. But if we choose to work in a different coordinate system, let's say the spherical coordinate system, where the variables are r, theta, and phi, well, in that case, x, y, and z themselves are functions of those r, theta, and phi. And that means that everything we have in the definition of the gradient needs to be rewritten in terms of those coordinates. To do that, for the partial derivatives, we need to use the chain rule. So for instance, dt dx using the chain rule becomes dt dr dx plus dt d theta dx plus dt d phi dx. Now dt dr, dt d theta, and dt d phi are the partial derivatives of t with respect to the new coordinate system, to the new coordinates. But dr dx, d theta dx, and d phi dx, we need to calculate them. And those can be calculated using the transformation rules we spoke about last time. We saw that r, theta, and phi can be written in terms of x, y, and z according to these formulas, and so we can just calculate each of those partial derivatives and plug them into this expression for dt dx. Similarly, we also need to do the same kind of calculation for dt dy and dt dz. So that's for the partial derivatives themselves. Now we also have the basis vectors, the unit vectors x hat, y hat, and z hat. They also need to be replaced by r hat, theta hat, and phi hat somehow. And to do that, we saw expressions for this last time. For instance, x hat was given by this expression here with r hat, theta hat, and phi hat. And we do the same thing for y hat and z hat. We also had expressions for them last time. And if we plug all of this into the definition of the gradient in Cartesian coordinates, the one I wrote at the top left, and we collect all the r hat terms, all the theta hat terms, and all the phi hat terms, we get this expression. So this is the expression for the gradient in spherical coordinates. You can do this for each of the special derivatives, gradient, curl, divergence, and Laplacian, and you can do it for spherical coordinates, you can do it for cylindrical coordinates, or for any other coordinate system you would work in. Notice that in this case here, for the gradient is not simply a vector whose components are the partial derivatives, it's the partial derivatives with some coefficients in front of them. Now there is no reason to learn this by heart. I will make a formula sheet on which you can find all the formulas that we discussed previously, all the ones you may need. And whenever I will use them during one of the videos, I will actually put it on the slide. But just know that you have them at your disposal. There will be a link at which you can find all those formulas. There is absolutely no reason to learn them by heart. So here is an overview of the formulas in the Cartesian case. So these are the ones as we discussed them previously. But if we now rewrite each of those, for instance, for cylindrical coordinates, what we find is these expressions here, involving again partial derivatives, but often with coefficients in front of them. And in the case of spherical coordinates, we get an even more complicated expression, which looks like this. And once again, there is no reason to learn this by heart. Just use the formula sheet whenever you need it. Having said that, I will use one of them already today, and I will put on that slide the formula when we need it. And additionally, if you try to actually go through the full derivation and try to work it out and you get stuck anywhere or anything is unclear, feel free to leave a message in the comment. So this is everything as far as those partial derivatives, as far as those special derivatives go. We will also need to be able to calculate integrals using integration by parts. Now, integration by parts for functions, for regular functions of one variable, is something we know, but because we need to generalize it, I will give you a quick reminder of how that works. So imagine we have two functions f and g, each of one variable. We multiply them and we want to calculate its derivative. Well, what you know from high school is that this is given by df dx multiplied with g plus f multiplied by dg dx. Now what we will do is we will isolate the last term here. So we will isolate f dg dx. This is equal to d dx of f times g minus df dx times g. And now we integrate both sides of this equality. So if we take the integral of this, we also need to take the integral of this here and of this. And then we use the fundamental theorem of calculus, which says that when we integrate a derivative, they cancel each other out. So the first term on the right-hand side just becomes f times g, and we find the formula that the integral of f times the derivative of g is equal to f times g itself minus the integral of the derivative of f times g. This is the formula for integration by parts for functions of one single variable. Now, for each of the special derivatives we discussed previously, there is a counterpart to this. Now, I will look at one of them specifically now, but in the formula sheet, I will put all the relevant ones for the rest of this course. But I will look at one specific one, and the one I want to look at is this one. One of the rules we saw for one of the special derivatives of a product was the divergence of a product of a scalar field f with a vector field v. And the divergence of f times v turned out to be equal to f times the divergence of v plus the dot product of v with the gradient of f. Now, what we will do is the same thing as before. We will integrate each of those here, and we take the volume integral of each of those. And I will use now the fundamental theorem for divergences, which says that the integral of a divergence over a volume is equal to the surface integral on the outer surface of that volume. And so because of that, the first term, which is a volume integral of a divergence of something, becomes the surface integral, so a two-dimensional integral, of the object itself that was within the divergence, so in this case, f times v. And now if we isolate the first term of the right-hand side, we find that the integral, the volume integral of f times the divergence of v is equal to the surface integral of f times v itself minus the volume integral of the dot product of v with the gradient of f. So this is one of those integration by parts formulas for the special kinds of vector derivatives, and we will need some of them during this course, and again all of them will be written in the formula sheet. I looked at this one specifically because I will use this one later on today in the course. Switching to the Dirac delta function, we start by trying to calculate the divergence of this specific vector field. So we consider the vector field 1 over r squared times r hat, and that's a vector field which points away from the origin, and the magnitude of the vector decreases quadratically as we move away from it. Now, if you look at it, you would think this is clearly a vector field with a positive divergence because the field is actually moving away from a point. But it turns out to be more subtle and a bit more complicated than that. Let's start by actually calculating its divergence. So how do we calculate the divergence? Well, the field itself is given in terms of r hat. That means that we're actually working in spherical coordinates, and so we need already one of those formulas we saw, namely the divergence in spherical coordinates. I wrote it here at the bottom right. And notice that that expression involves derivatives of Vr, V theta, and V phi. So V theta and V phi, so the theta and phi components of V, are 0 for this vector field. The vector field only has a term of the form something times r hat, so it only has an r component, and its r component is 1 over r squared. So if we plug in 1 over r squared for Vr, what we find is 1 over r squared times ddr r squared times Vr, which is 1 over r squared. Notice within the brackets we have r squared times 1 over r squared, so that's just 1, and the derivative of 1 with respect to r is 0. And so we find that the divergence of this vector field is 0. So that is already quite unexpected, because again, purely based on visuals, you would expect the divergence to be positive here. But it becomes even more unusual and unexpected when we try to calculate the surface integral of this vector field over the surface of a sphere of radius r centered at the origin. So to do that, we need to have an expression for dA, and remember that dA is a tiny portion, a tiny element of the surface of the outer surface of the sphere, and it points outward because it's a closed surface. And the expression for dA is r squared sine theta d theta d phi, and it points in the r hat direction, so away from the origin. If we plug this into the expression, we have v dot dA. V is 1 over r squared r hat, but notice that because we are on the surface, the value of little r is actually the radius of the circle, so it's 1 over capital R squared r hat, dotted with dA, which is r squared sine theta d theta d phi r hat, and it's a double integral, it's a surface integral, and the r hat dot r hat is 1. So we're left with the product of the coefficients in front of them. The capital R squared divided by capital R squared is 1. So it also vanishes. Well, it's not vanishing, it's just 1. And we're left with a double integral of sine theta d phi. And notice that those two integrals are independent, so we can factor them. And we get one integral over theta, namely sine theta d theta from 0 to pi. And we get a phi integral from 0 to 2 pi of d phi. Now the phi integral just gives us 2 pi, and the integral of sine theta d theta is negative cosine theta, evaluated between 0 and pi. Cosine of pi is negative 1, so we get negative negative 1, which is 1, plus cosine of 0, which is 1, so we get 2 times 2 pi, which is 4 pi. So notice that the integral from 0 to pi of sine theta d theta is 2, because we will need it later on today again. So on the one hand, we found that the divergence of this vector field is 0. On the other hand, we found that the surface integral over the surface of this sphere of radius r centered at the origin is 4 pi. And that is weird because we also saw the fundamental theorem of calculus, which said exactly this, that the volume integral of the divergence is the surface integral of the field itself. Now the right-hand side, the surface integral of the field is 4 pi. But if the divergence is 0, how can its integral be 4 pi? To answer that, we need to look at something known as a Dirac delta function. And we will come back to this in a couple of slides once we understand the concept of the Dirac delta function. We first look at the following function. I define r1 of x as a function that is 0 outside of the interval negative 1/2 to 1/2, and within that interval it's simply constantly 1. So we get a rectangle, and the integral of this function r1 of x is the area of that rectangle, which is its width times its height. Its height is 1 and its width is 1, so its area is 1. Now what I will do is I will make the rectangle narrower but at the same time higher. So I will double its height but half its width. And I get a new function r2 of x, which has a height of 2, a width of 1/2 going from -1/4 to +1/4. And outside of that interval -1/4 to +1/4, it is 0. And its area remains 1. Now we can keep on doing that. We narrow and we make the rectangle narrower and narrower, but at the same time heighten it in such a way that its area does not change. If we keep on doing that indefinitely, we will get an infinitely high and infinitely narrow rectangle of area 1. That is what we mean when we say the Dirac delta function. So a Dirac delta function is something which is 0 everywhere except at the origin where it is peaked, and its height there is infinity. So in such a way that its area is 1. So this is known as the Dirac delta function. Now I do have to say, whenever we use the name Dirac delta function, mathematicians' hearts bleed. This is not an actual function. Functions are objects in mathematics that are defined in every single point of their domain and have an actual value there. But this is not such an object because it's 0 everywhere. That is completely fine outside of the origin, but at the origin its value is infinity. Now infinity is not a value, it's not a number. So this is not, strictly speaking, a function in the mathematical sense of the word. This is something, this kind of object is studied in mathematics and it's a well-defined object, but it's not a function. It's the technical name for it is either a distribution or a generalized function. Now, because it is so common to use this, to give this object the name of the Dirac delta function in physics, everyone in the physics community knows it as such, and I will use the word function for it. But keep in mind, this is not a function as mathematicians understand the word function itself. Now, having said that, it is a mathematically well-defined object if thought of as a distribution. And as such, we can use it in integrals. And you may as well think of distributions of delta functions, for instance, as things that always need to go within integrals. What do I mean by that? Well, take some function, let's say an actual function, f of x, which is a good old function like we're used to from before we learned about delta functions. And we want to calculate the integral from negative infinity to positive infinity of fx delta x. Now notice that the delta x itself is 0 everywhere except at the origin. So no matter what the value of the function f is outside of the origin, it will not affect the value of the integral. The only value of f that is of interest to us when we calculate this integral is its value at 0. So I may as well replace f of x by f of 0 because its value everywhere else is just not important. It gets killed by the 0 of the delta x. Now, once we are in this form, we can just plug out, take the f of 0 out of the integral. And we're left with f of 0 times this integral, which by the definition of the delta function is 1, and so we're left with f of 0. Notice what the delta function actually does. When we integrate f times delta, what we're left with is the value of f at 0, at the point where the peak of the delta function is. So it picks out the value of f at its peak. Now it is important that the peak is in there, but the actual integration boundaries are not important once the peak is in there. What I mean by this is the following. We integrated it now from minus infinity to plus infinity. But I may as well have integrated from minus 21 to 7, for instance. If I integrate the delta function from negative 21 to 7, I still get 1 because the area is completely concentrated at the origin. So as long as the origin is in that range, the value of the integral will still be 1. If we, on the other hand, integrate the delta function, but in a range that does not include the origin, so does not include its peak, let's say from 5 to 392, well, the value of the delta function in that range is 0 everywhere, and so its integral will also be 0. Basically, no matter which strictly positive epsilon I take, if we integrate it from negative epsilon to positive epsilon, that range includes the origin, and so the integral of the delta function will still be 1. Now, there is nothing special about the position of the peak. We chose it in the definition of the delta function to be at the origin at x is 0, but we may as well have put it at a value of x is a. So there is absolutely nothing special about that 0. And so if we take a delta function peaked at a, the value of the delta function is 0 everywhere except at a, and at a it's infinitely high, and its integral will still be 1, given that the value x is a is within the integration range. So, and just like before, if we integrate f of x times a delta function, this will pick out the value of f, but not at 0, but at the position of the peak, so in this case at a, so we get f of a here. Couple of examples. If we integrate from negative infinity to positive infinity x cubed minus 2x plus 5, multiplied with the delta function peaked at 1, what we will get is the value of that cubic function at x is 1, so we get 1 cubed minus 2 times 1 plus 5, which is 1 minus 2, which is negative 1, plus 5, which is 4. Second example, if we integrate from negative 20 to negative 5, the tangent of x times the delta function peaked at negative 4. Delta of x plus 4 is a delta function peaked at x is negative 4. Well, negative 4 is not in that interval. It's to the right of it. And so the integral gives us 0. And finally, if we want to integrate from negative 4 to positive 15 ln of x, delta of x minus 10, delta of x minus 10 is peaked at 10, and so all we're going to get, 10 is in that interval, and so we're going to get the value of ln evaluated at 10. So that's ln of 10. So this is how to work with one-dimensional delta functions. Now, the first time you encounter a delta function, it may look like a quite unnatural and useless object. So I want to give you a motivation for why it is that it's actually a very useful tool to have in physics. So we consider a rod of length L and mass m, and we define its linear mass density as that mass divided by its length. So lambda, the mass density, tells us how much the mass is per unit of length. We now take the rod and divide it into smaller pieces, and we choose an x-axis along the rod with the origin at one end, in this case the left end of the rod. Now, if the mass of the rod is homogeneous, then the mass density in each of those pieces is the same. But if it's not, if some parts of the rod are heavier than others, then lambda, the mass density, becomes itself a function of x. For each value of x, you may have a different value for lambda. And now we choose one of those small pieces. Its size is dx, and its mass, which I call dm, is then by definition lambda times dx. Now again, lambda is a function of x. If we now want the total mass of the rod, we need to add all those dm's up together. And that means that we're integrating dm over the rod, over the length of the rod, which is an integral over the rod of lambda x dx. Now, this is an integral from 0 to L because I put the left end of the rod at 0, and so its right end will be at x is L. But if we now define lambda to be 0 outside of that range, so left of 0 and right of L, the value of lambda is 0, we may as well take the integral from negative infinity to positive infinity. And so m can be thought of as the integral over the whole of space, in this case it's a one-dimensional space, of the linear mass density lambda. And now we want to use this expression for the mass, but for a point particle. So imagine we have a point particle of mass little m at the origin of some coordinate system. Now, if we want to write its mass as an integral from negative infinity to positive infinity of lambda, what function of lambda can we choose to do that? Well, first of all, lambda has to be 0 everywhere except at the point where the mass is sitting. So lambda is a function that is 0 everywhere except at the origin. Now, if at the origin lambda had a finite value, then its integral would also be 0, because if we integrate a function that is 0 everywhere except at one point, and at that point its value is 17, let's say, its integral will still be 0, because integrals don't see finite values at one specific point. And so what we would get is 0. To actually get a value out of this integral that is non-zero, we need to make the mass density infinitely high at that point. And that is exactly what a delta function does. So if we define lambda as the mass of the particle m multiplied with delta x, and we plug that into the integral, what we get is what we want to have. Namely, we can take the m, pull the m out of the integral, and we are left with m times the integral of the delta function from negative infinity to plus infinity, which is 1, and so we get m. So delta functions are used to describe properties of point particles, whether it's a mass like I did here, or as we will often do, charges in the context of electromagnetism. Anytime in physics we want to describe point particles, we need to have properties of those point particles that are zero everywhere outside of the particle, but the particle is a point, and so that value has to be there and nowhere else. And in order to be able to describe it using integrals, it needs to have an infinite value at that point. And so every time we describe point particles, you will have delta functions in that description. That is one of the main reasons we need delta functions in physics. We also want to define what it means for expressions involving delta functions to be equal to each other. So imagine we have some expression involving a delta function, something like this, x times the derivative of a delta function. Now a delta function itself is already quite ill-defined. What do we even mean by its derivative? Well, we will see on the next slide how to give meaning to such an expression. But more generally, if we take some expression involving delta functions, let's say d1, and another expression d2, also involving delta function, what does it mean for them to be equal to each other? Well, for a regular function, equality would simply mean that plugging in any value of x to both sides of this equality would give the same value. Now, this in principle is still true for delta functions. The problem is that delta functions are infinite at certain points, and saying that two infinite things are equal to each other is not really a well-defined concept in mathematics. And so because of that, we take a more general approach to equality. We say that d1 and d2 are equal to each other if the following is true. Take any ordinary function. When I say any ordinary function, I mean any function that does not involve delta functions, and of course one that has an integral where this integral is defined, because otherwise it's a meaningless statement. But we say that for any function we would take, whether it's a sine or an exponential or some polynomial or anything of that sort, if we integrate f times d1 and we integrate f times d2, they need to be equal to each other for any such f. If that is true for any f, then we say that d1 and d2 are equal to each other. So let's see how we can use this. If I look at the delta function of negative 3x plus 2, remember the delta function is zero everywhere except at its peak where it's infinite. So the peak of this is at the zero of negative 3x plus 2, which is at x equals 2/3. So you may think that this is simply equal to delta of x minus 2/3. Now it turns out not to be exactly true. So what is it equal to? Well, to check that, let us integrate from negative infinity to positive infinity f of x times delta of negative 3x plus 2 for some function f. Now I will do a change of variables. I will define y as negative 3x plus 2, which is equivalent to saying that x is equal to 2 minus y divided by 3, and therefore dx is equal to minus 1/3 dy. And we plug this into the integral. So we get the integral of f of x, which is f of 2 minus y divided by 3, times the delta of y, times dx, so times minus 1/3 dy. Now the boundaries, when x goes to negative infinity, y goes to positive infinity, and vice versa, when x goes to positive infinity, y goes to negative infinity. Now, the minus 1/3 can be brought out of the integral, and the minus can be used to actually switch the boundaries again. So we get 1/3 times the integral from negative infinity to positive infinity of f of 2 minus y divided by 3 delta y dy. And this gives us the 1/3 remains, and all we're left with is the value of f of 2 minus y over 3, where we plug in for y the value of the peak of y, which is the peak of y is at y equals 0, so we plug in 0 for y and we get f of 2/3. Now notice that this is the same expression we would have gotten if we had integrated from negative infinity to positive infinity f of x, but not simply with delta of x minus 2/3, but with 1/3 delta of x minus 2/3 dx. And so according to the definition we gave above, the delta of negative 3x plus 2 is equal to 1/3 delta of x minus 2/3. And so these two expressions are the same according to this definition of the word equality. As an additional example, let us look at what the meaning is of this expression. So what we will do is we will integrate from negative infinity to positive infinity some function f of x multiplied with this expression, so multiplied with x d dx of delta x dx. And what we will do is we will use integration by parts of regular functions of one variable, and as we saw earlier, integration by parts is given by the integral of f times g prime is equal to f times g minus the integral of f prime times g. And as g prime, we take this whole thing here. So the derivative of the delta function is what we will use as g prime, and so the rest f of x times x will be f. And so if we apply this, we get f, which is f of x, times g, and g is the antiderivative of the delta function, which is simply the delta function itself, and that needs to be evaluated at the boundaries, which is negative infinity and positive infinity, minus the integral from minus infinity to plus infinity of the derivative of f of x times x, so that's d dx of f of x times x, multiplied with g, which is the delta function, dx. Now, first of all, the boundary term, notice that the delta function is 0 everywhere except at its peak. So when we take the limits for x going to both minus infinity and plus infinity, this will go to 0. So the boundary term just vanishes, and we're left with minus the integral from negative infinity to positive infinity of the derivative of f of x times x gives us f prime of x times x plus f of x times 1 multiplied with the delta function dx. And now what we're left with is the value between the square brackets where x needs to be plugged in, we plug in a value of 0 for x. So the first term there, f prime of x times x, just vanishes because x is 0, and so we're left with negative f of 0. And notice that this is the same thing we would have gotten if we had integrated f of x, but not with delta x itself, but with negative delta x. So according to the definition of equality, what we find is that x times d dx of delta x is equal to negative delta x. So this is the way in which we will work with delta functions, expressions involving delta functions, and their equalities. We also need the three-dimensional counterpart of the delta function, and so we define the three-dimensional ones, which we write as delta with a 3 on top, as the product of three one-dimensional delta functions, so delta x, delta y, delta z, and we think of it as a function again in 3 dimensions, which is 0 everywhere in this 3-dimensional space except at the peak, in this case at the origin, and it has an infinite peak at that point, in such a way that the area under that peak is 1, just like we had with one-dimensional delta functions, but in this case we have a volume integral, a 3-dimensional integral. And just like with the delta functions before, if we integrate not the delta function itself, but f times the delta function, what it does is it picks out the value of f at the point where the peak is. So in this case, the peak is at a point denoted by the vector a, and we get f of a. And so now we can actually go back to the question that led us to the delta function in the first place, which was the following. We considered a vector function v given by 1 over r squared times r hat, and we saw first of all that its divergence is 0. Now notice that we actually only calculated it for r not equal to the origin. So everywhere away from the origin, the divergence is indeed 0. But at the origin, that divergence is not really well defined. The function itself, the field itself, is not really well defined. It diverges there. But at the same time, we also saw that its surface integral, which is equal to, according to the fundamental theorem of calculus, to the volume integral of this divergence, is equal to 4 pi. Well, this is exactly what a three-dimensional delta function would do. It is zero everywhere except at a point, and at that point its peak is infinite in such a way that its integral gives us some finite non-zero value. And so we get this. It turns out that this actually has the properties we need, because it's true that the divergence of this is zero everywhere. It's true that the delta function is zero everywhere except at the origin, but in such a way that at the origin it is infinite in such a way that when we integrate this over all of space, we indeed get 4 pi. So the divergence of this specific vector field turns out to be exactly equal to the three-dimensional delta function times some coefficient, in this case 4 pi. As an example, I want to work out one specific integral, namely the volume integral of this field, which is r squared plus 2 multiplied with the divergence of this 1 over r squared times r hat. And to show you the power of this delta function approach, I will calculate this integral using two different methods. The first one will be the delta function approach. Now I want to calculate this integral over the volume of a sphere of radius capital R centered at the origin. Notice that indeed the divergence of 1 over r squared r hat is exactly the expression we found, which is 4 pi times the three-dimensional delta function. And so if we apply this, we find that this integral is equal to the volume integral of r squared plus 2 times, and I replace this divergence by this three-dimensional delta function. So we get 4 pi times the three-dimensional delta function r d tau. And what this gives us is 4 pi times the value of r squared plus 2, where we have to plug in for r the value of r where the peak of the delta function is, which is the origin. So we plug in 0 for r, and so we find 4 pi times 0 plus 2, and so we find 8 pi. So this is the result of this integral using the delta function approach. I will calculate it now using a completely different approach. I will calculate the integral using integration by parts, and as we will see, we get the same result, but it will be much more involved. So remember, one of the formulas I described earlier this lesson was this formula for integration by parts involving divergences of vector field. Now notice that is exactly the kind of integral we have. We have r squared plus 2, which plays the role of f. So this is our scalar field, and 1 over r squared times r hat will be our vector field v. And so if we apply this formula we found for integration by parts, we find here the surface integral over the surface of that sphere of radius r of f times v. Now f is r squared plus 2, but because we are on the surface, r can be replaced by the radius, which is capital R. So we get capital R squared plus 2 multiplied with v, the vector field v, which is 1 over r squared times r hat. And again, the r squared in the denominator is again on the surface, so it's 1 over capital R squared r hat, dotted with dA. And we are on the surface of a sphere, and we saw earlier already today that dA on the surface of a sphere is given by this expression. So we get r squared sine theta d theta d phi r hat. So this is the first term in the integration by parts formula, minus the volume integral of v itself, which is 1 over r squared times r hat, dotted with the gradient of f. F is r squared plus 2, and we need to calculate its gradient. Now, the gradient in spherical coordinates was given by this expression, and again, the scalar field t does not have, in our case, a theta or a phi dependence. In other words, we're only left with the first term, which is the partial derivative of that function with respect to r times r hat. And so if we take the partial derivative of r squared plus 2 with respect to r, we're left with 2r times r hat times d tau, and d tau is r squared sine theta dr d tau d phi. And now we can calculate all of this. In the first term, the r squared in the denominator and the r squared in the numerator cancel each other out, and we can pull r squared plus 2 out of the integral, so we are left with r squared plus 2 times the surface integral, which is a double integral, over r hat dotted with sine theta d phi r hat. Now r hat dot r hat is just 1, and so we're left with the double integral where theta goes from 0 to pi and phi goes from 0 to 2 pi of sine theta d theta d phi minus the volume integral, which is a triple integral. R goes from 0 to capital R, theta goes from 0 to pi, phi goes from 0 to 2 pi of, well, the r squared in the denominator and the r squared in the numerator cancel each other out. The 2 can come out of the integral, and we're left with r hat dot r hat is still 1, so we're left with r sine theta dr d theta d phi. And so we find r squared plus 2 times, well, the phi integral just gives us 2 pi, and we're left with the integral of sine theta d theta from 0 to pi, and it's the integral we calculated earlier, and we found that it was equal to 2, minus twice the triple integral. Now notice that each of those integrals, the r, the theta, and the phi one, are independent of each other, so we can factor them, and so the r integral gives us r squared divided by 2. At the boundaries is capital R squared divided by 2, times the sine integral gives us another 2, and the phi integral gives us 2 pi. And so we find 2 pi times r squared, sorry, that's 4 pi times r squared, plus 8 pi minus 4 pi times r squared, which is the same 8 pi we found on the previous slide. But this is a much more involved, much more complicated calculation to get the same result. And so that shows some of the power of using delta functions to calculate integrals. A final point I wanted to discuss today is the following. We know that electric and magnetic phenomena are given by these 4 equations, the Maxwell equations. But we are not given E and B themselves, but their derivatives, their curl and their divergence. The question is, does this determine them? Is it sufficient to know the curl and the divergence to know all we need to know about them? So more generally, imagine we take some vector field f, and we are given not f itself, but we are given its divergence, namely the scalar field D, and its curl, the vector field C. Does this determine f uniquely? Now, these are differential equations, and just like we always have with differential equations, and don't worry if you haven't seen differential equations before, but with differential equations, you always need additional boundary conditions. But even then, the question is, do we know everything we need about these fields? And so there are a couple of theorems that I want to mention without proving them here, but just mentioning the fact what those theorems say, which will help us understand what we need to know about those fields. So the first theorem says the following. If the curl of a vector field f is 0 everywhere, that is equivalent to saying that when we take the line integral of that field over some path between 2 points, between a point A and B, the result will be independent of which path we chose between those points A and B. It only depends on A and B themselves. Equivalently, the closed line integral over any closed loop will always be 0. And finally, it's equivalent to saying that f can be written as the gradient of some scalar field. Now there is a minus sign in front of the gradient here. That minus sign is purely conventional. We may as well have absorbed the negative sign into v, but because of historical reasons, we always put a minus sign out of it, and this v is usually known as the scalar potential, and it will actually have a physical meaning that we will use in electromagnetism. But so the main point here is that saying that the curl of a field is zero everywhere, so if we know that the field has a curl of zero everywhere, and such fields are known as irrotational fields, then that field can always be written as minus the gradient of some scalar field, v, known as the scalar potential. Similarly, if we know that the divergence of the field is zero everywhere, then given some boundary line, the surface integral of that field over that surface is independent of what the surface is, but only depends on what the boundary line is. Equivalently, it also says that for any closed surface, the surface integral will be zero, the closed surface integral will be zero. And most importantly for us, it says that if the divergence of the field is zero everywhere, then the field can be written as the curl of some vector field A, and that A is then known as the vector potential. So if the divergence is zero, the field can be written as the curl of something, and if the curl is zero, the field can be written as the divergence of something. And there is a general theorem known as the Helmholtz theorem, which tells us that any field, when I say any field, again, there are mathematical conditions for both previous theorems as well, of course. It needs to be well defined, I mean, in the sense that we need to have functions that are smooth enough such that their integrals and their derivatives are well defined, etc. The paths, the lines over which we're integrating also need to have certain smoothness properties. All of that will be always true for anything we will look at in this course. But under those conditions, any field, independent of what its curl and its divergence is, can be written as minus the gradient of some scalar field plus the curl of some vector potential. And that will be very important for us in electromagnetism. This was it as far as the mathematical introduction goes. From the next lesson onward, we will actually go and look at the physics of electromagnetism. I hope to see you there. I'll see you next time.